Okay, so this is the first video on this. It's on OceanShader. I'm going to take you through the steps that I went through to produce this. Not so much in the typical form of a tutorial, similar to my other shader video that I went through with the hollow glitch shader, where I'll show you everything that I put together and give you a little bit of information of what I've done, but it's not a full-on tutorial. So first off, I want to point you in this direction, which was this video that started me researching it in the first place. He talks about the stylized VFX that were in Rhyme, and the complexity of the OceanShader towards the end pops in, and it's got some interesting things, and I thought it would be a nice project to sit down and try and come up with something. And he points to these Gerstner waves, which are kind of cool, and they're essentially math. And so there's a paper about them, which everyone points you to, which is here. That's this NVIDIA paper on creating them. And of course, you scroll your way through it, and like get to sine wave. It's pretty straightforward. Sine waves are not really that difficult to reproduce, graphically speaking. You can create just a gradient, right? That's going from black to white, then to black again, and you get that kind of effect. And if you go with something along those lines, you could even say, well, this is black down here, and then just go all the way up, and that's black, and it's going to push outwards, and then you can offset that if you want. Then you can of course scale the texture to get the wave width, and you just increase the intensity basically by multiplying it against a whole number to get much stronger. You can use things like powers, exponents, etc. to change this. So you can use a lot of the same sort of stuff without having to necessarily build them math-wise. The advantage to using math in an ideal situation is that it prevents you from having to deal with resolution. It can save you on memory, but it may increase calculations. And so when you go through things like the Unreal nodes, math nodes, it talks about like some of them are super cheap to use, so that they're not so expensive. So it's a pick your poison kind of deal. Anyways, we get these equations, and it talks about the equations and how this whole thing works, and then you have to try and rebuild these equations based on what's here. And there's of course the Tessendorf, I think it is, waves, which I attempted after doing these Gerstner ones, and my brain imploded, and yeah. So that's my one note about dealing with this stuff that's essentially math-based, is that you can only go so far without having a deeper knowledge of math before it's just gonna not work out for you. Anyways, so the first element of this is the Gerstner waves, and if you want to recreate these based on what's here, again, you can use gradients to do much of this. You don't have to do it this way, but there's some important elements to it. So number one, we're using sine and cosine, and the reason for that is that where you see the blue and it overlaps to white is the height information, and then we also have this stuff that will go ahead and pinch the wave, and so it's going into negative as well as positive values in order to make this whole thing kind of work. So math is giving you that advantage straight off the bat. So if we go down in here, we start off with wave direction, and wave direction I've changed from other examples. I had to look at a whole bunch of different things that people had done to try and get this to work, and some of the changes I made were in particular adding a noise to this where I could get a little bit more distortion off it, so it's not just a straight line, which I find kind of useful, but I have to use it in very small amounts. So I have my wave direction here, which is I have an input which can go into this, and I use that later on. It's running through, I've got this 0.5 that goes through this, So the noise and this are added. I'm also using this lerp here with an input to change how much distortion. So I just I preset the scale. One thing that I could use to make this maybe better is maybe have something in here to change the scale of the noise, so affect that. That would be one thing that I could do to make this perhaps an overall better shader. But I preset a scale that I was comfortable with regular Unreal scenes, and then work with that. And so this lerp is controlling how much of this noise is going into this. I then proceed to mask out the red and green channels, and that's because we're using X and Y information to control the direction. In other examples of this, where other people have tried to build this overall setup, it's basically just been a two-color input, or two-value input rather, like a two-vector, and they just change the numbers in order to get the direction, or they'll use like a three-vector where they'll use a color and they'll like manually try and pick it. I wanted something that was a little bit simpler, just a single thing, and that gave me rotation that would be 360 based on like I guess a -1 to +1 value. So that's what the input is. So we take that information and then we invert them, and then we make a new float from it. So then passing through, we have our absolute world position, mask, and a dot product in order to help us set that up. And these each are labeled. Below that we've got another tiny little section, and I'll show how these are connected over in a moment. So this is our wave width, starting off with a default of 20, and then we have pi, which is nice to know it's in there. You can use the actual pi, or you could type in a number if you wanted, but pi exists inside of Unreal. Who knew? And then some arbitrary multiplications. I played with some numbers that I thought were nice, and then I let this do the rest of the work. Next we go down here, and of course remember you can pause this at any point, go back a step if you want to kind of follow along. Maybe pause and get a cup of coffee and start building this in Unreal yourself. So there's again another default to initially set a base speed, and then I can change that to whatever I want. So we've got our wave width, which is in here, and it's being multiplied against time plus this number. So coming off the wave direction and the wave width, we multiply those together, and then we take all that information, we multiply this together. We also take this wave width information and multiply it against this speed in order to get this to work, and we end up here. And this is an add, not a multiply actually. So this is a multiply, this is our add. Next down we have our num waves. Now this exists in it, this exists in various other little tutorials. This has to do with the pinch. If this value is incorrect, your pinch is very difficult to use. So setting this to a larger number means that you have more play with the wave, I think I call it wave steepness, or pinch. Is just basically the whether it's rounded or if it's pinched at the top. So this, probably you just want to find a number and just kind of lock it down. So I do have an input here, but I've ended up changing it to a default value, and that works for me, which I think it's around 20. But you can play with it and you'll see. Anyways, this comes up and goes into this multiply, which is coming off the wave width, into multiply here, and that one is coming down through here, which is our wave height. So this wave height goes out a few times to different multiplies. So we've got a multiply node here, which is going off to a sine and a multiply over here. We also have it coming up to these two multiply nodes, which go into this divide node, which is our steepness. So that's what I was talking about, that other value. The num waves helps you with this value to actually get it to behave, otherwise it does some pretty bizarre stuff. And then of course that goes down into another multiply, which is coming off of that wave height again. And that goes into a multiply and a cosine. So this is getting our x and y components off of the stuff here. These go into multiplies, and they come around from masks. So our green and red channel, which are again coming from this. So you have your red and green channel come down over here from your x and y components and multiply, and they go into the top part of the make float. And then our z components, which is a sine wave. So you have cosine, which is an offset, and sine, which is the main one, and that's where you see this offset. So the blue is this guy right here, and then what looks like yellow is actually red and green combined together, and where they overlap it's white, and that's the cosine, which gives you an offset. So all of this goes together in order to create your typical wave. So if you make sure that you give your inputs in there, which is a simple matter of input function input, and then you just label it as you see fit. And all of these, I believe, for the most part, I've switched to scalar so that they're a singular value. And that's about it. So this is this material function down here. So again, you right click and you create a material function, and this is going to be used in the next video to create the starting of this. So we'll post the next video in a little bit, and hopefully you can muddle your way through this first part, and the second part will be much the same.